Welcome to the motion graphs lesson. So we've been looking at acceleration, position, and velocity, looking at these three ideas and what does it look like in a graph. So that's what we're going to look at today, is looking at that graphical representation of this idea of motion. All right, let's get started. So this is kind of what a typical motion graph would look like. You have velocity in the y direction and your time in the x. Now 95% of the time when you're looking at these problems, time will always be on the y-axis. So your velocity, your acceleration, your position, all that will be plotted in the y direction. So it'll kind of give you this nice, neat path to follow. All right, and so you kind of just look here. So at the value at time 0, what is the value at 0? Oh, look, the red line matches 0 velocity. All right, time 4, match it up, 3 meters per second. All right, so this just kind of keeps a good idea. This is going back to Algebra 1, so super simple stuff here. All right, now the good news is that under the line a lot of times is still valuable information. And so typically under the line will help me understand typically the change in position. If I'm still looking at a velocity graph or an acceleration graph, I can really use some good information. So I could, if it's a rectangle, I could use geometry with base times height, triangle, 1/2 times the base times height, or we can use the average velocity times time, getting that is the same. This is nice, easy way. It's good information to understand. Another equations that will help you understand calculating this. Again, I'm trying to think back and like really use your algebra skills and just kind of remind you of those things. So just seeing that you can calculate your slope in 3 different ways, and they represent 3 different things, but they represent the exact same number, which is very important. So however, if you're looking at this graph, whichever way is best way for you to calculate the slope, do that. There's no right or wrong way. Now, this is probably the most important slide about this whole video, and I want to make sure that you get it and get it good. All right, so make sure you take a picture of this, write it down, whatever you need to do, but this is by far the most important slide of this video. All right, and so it's just taking the 3 types of graphs and looking at all the information that they want, what they can provide and what you might want to know in the future. So looking at the position versus time, it is the axis is x, which is position versus time, so therefore it'd be meters and seconds. So the slope of the line that's plotted would be my velocity, which is delta x over time, which would be the equation that we use for velocity. The area under here is really null and void. I don't need to know it. It doesn't give me any information when I'm talking about motion, so we're just going to ignore it for now. Velocity versus time, you can see its position, how it calculates acceleration as the slope of its line. However, the area under the velocity versus time graph will give me the change in position. Very crucial. Physics questions love to tackle and look at these graphs and like what is the change in, or what is the position or the displacement of the object looking at the graph. Well, if it's a velocity versus time graph, I can figure it out real quick, just find the area. Acceleration are weirdly looking graphs. They're just horizontal lines. So we'll show you an example of that in a little bit. But it's just horizontal lines, and the slope of the line is actually meters per second to the cube, or to the third, so meters per second cubed, and it's actually called a jerk because it's, why would you want to know it? It's kind of weird, so guess what? You don't need to know. The slope of the line will mean nothing to you, so just don't ignore it. However, the area is important, and it tells you the change in velocity. So here, this is a velocity versus time graph. This is an example graph. Just kind of want to explain a few key things when you're looking at a graph. So the velocity and time. So thinking about actual motion. So when I look at my first few moments of this graph, it's a linear line. So telling me that the velocity is changing in a linear motion. So I'm having a constant acceleration right at this moment. And then it stops accelerating, but I still continue at that 3 meters per second, all right? And I have that constant velocity, so a flat horizontal line is constant velocity. And then you see that I have a deceleration that's constant, all right? And eventually it comes to a stop here at 0, and it keeps going. And then whoever's driving or whatever's going on decides to accelerate onward. So that's just kind of a quick way of understanding what's going on with the motion, all right? So again, slope is acceleration, under is delta x, tells me how far away I'm getting away from my origin. So here's an acceleration versus time graph. Computers really don't like these graphs because they always have to add this extra line here. And this line actually doesn't necessarily exist. It's just these horizontal bars. All right, and there's actually one right here that you really can't see, so it's actually kind of stair-stepping down. And so if it's in the positive, right, it means that my acceleration is increasing, so I'm accelerating. If I'm at 0, this is the tricky part, all right? This could mean that the object's not moving, or it could mean that this object is moving at a constant velocity, all right? So if I'm up here and I'm moving, and then I go to 0 acceleration, then I'm still moving at whatever that velocity was at this moment here. I'm just not accelerating. And then when I came down here, I started slowing back down. All right, so that's kind of how that works. This is the little tricky part about the acceleration, is that you have to remember that it's about the velocity before it reached that 0. If it was 0, then it still is 0. But if it had a velocity before the acceleration graph hit 0, then the velocity remains constant. All right, so I want to do one little example with you, just kind of basically go from acceleration to velocity to position to graph. All right, it's super simple. You'll kind of just see how these three graphs relate. Now, I made this acceleration graph by myself, so therefore it looks a little better. You actually can see that there is no vertical line connecting the dots. And I just basically kind of remade the graph that we just looked at. I just want to show you kind of what's going on. All right, so my velocity is increasing uniformly at a constant acceleration upward, and then it stops accelerating. So I just do a nice horizontal line for some amount of time, because I don't know, I'm just kind of eyeballing here. And then the vehicle or object then deaccelerates back to 0. Okay, so that's kind of how the velocity would work. Now, position, if I'm going all the way back, position is going to look quite a bit different, all right? And so here I'm accelerating, so my velocity is changing, so that's actually exponential in the position form, and then it goes to linear because it's traveling at a constant velocity, and then he decelerates, so then it's going to be exponential back to 0 to stopping. And so that's actually kind of how that graph would look if I'm looking at acceleration to velocity to position. And so if you're doing that, your position graphs are going to start looking just a wee bit weird. It's completely doable to find out all the information you want, but that's just going to be for a later lesson. Good luck.